Hello, I'm Cláudio. I'm here to present our work on application of the Functional Mockup Interface standard for co-simulation to the domain of seismic hybrid testing. This work has been developed together with Giuseppe and Peter, both from Aarhus University, but from different departments. Giuseppe comes from the Department of Civil and Architectural Engineering. So, to motivate, why is it important to do hybrid testing? I will show you the traditional method for evaluating whether a structure can actually withstand a particular earthquake, and I will let you just find a time point. This is an example where three structures are being evaluated regarding earthquake. And as you can see, for example, there's more structural elements here, so this house can withstand better an earthquake. Now, why is it that hybrid testing that involves coupling a virtual simulation with a physical prototype, why is it so important compared to the traditional method? Well, as one viewer of this video pointed out, they destroy a whole house each time an experiment is run. So, cost. We have, for this, in order to study this new method of evaluating civil structures, we have developed a prototype at Aarhus University for hybrid testing. You can see the picture of the prototype here, and it consists of a physical subsystem consisting of a wall and a beam, and actuators, hydraulic actuators that can displace this beam. And these hydraulic actuators come with force transducers that allows us to measure the reaction force when bending the beam. Of course, this is a prototype, and it is representative of a real hybrid testing experiment. The cool idea of hybrid testing is that this actuator is connected to an industrial PC, which then can couple this physical subsystem to a numerical, arbitrarily complex structure. One of the key insights into the particular example we run today, we used in this for these experiments, is that the simulated system also includes the mass of this beam, and that means we are able to run an experiment that could take, in the real wall clock time, could take 10 seconds. We are able to, for example, do it in 200 seconds. So we are able to emulate, because the displacement of the bar is independent of the time, the rate at which time passes. We are able to simulate the remainder of the forces, the inertial forces and the damping forces. Both depend on velocity, which depends on time. We are able to simulate them, and that means we can slow down our experiment and do it in a safe, controlled way. But in general, hybrid testing can be done in real time. This is a video of the numerical results we obtained along with a recording of the actuator, and as you can see the displacement here on the left, and you can see the corresponding measured force by the force transducer. You can see effects that are very difficult to model in practice. You can see them here, such as hysteresis. Now, this is representative of a large-scale hybrid testing setup because one of the co-authors has been involved in producing a large-scale experiment involving pillars of the Clio bridge, and you can see all about it in the details here below. Now, what are the challenges in hybrid testing? The ones we are tackling is the fact that it is very difficult to quickly set up the experiment, and this is because we have different numerical simulation environments, because we want to simulate different numerical substructures. There are different interfaces. If you consider two different labs who have as a hybrid testing setup, then there will be two different interfaces to communicate with the actuator controller. This also demands some standardization. These two elements make it very difficult to reuse coupling algorithms, which have to be developed very carefully because they have to guarantee stability. It's easy to imagine what happens if this thing becomes unstable. Now, right now, in the domain of hybrid testing, as far as we know, this kind of experiment is done with ad hoc interfaces that are just coded on the spot in order to enable co-simulation. And our contribution is to propose and evaluate the functional mockup interface as a standard interface to tackle these challenges. Start with some terminology. I assume the viewers are familiar with the functional mockup interface standard and some terms like the functional mockup unit. We just recall here that there are two interfaces under the functional mockup interface standard. One of them is the model exchange, where the FMU acts as a differential equation which outputs accelerations and the derivative of the state, and importer, which is the tool that imports and interacts with the FMU, is then responsible for estimating the next state of the FMU. In the co-simulation interface, it's the FMU that is responsible for estimating its next step. And so the importer here is a lot simpler. It simply asks the FMU, give me your next state. We need to distinguish the term coupling from the term orchestration algorithm because in practice, most of the times we only have an orchestrator algorithm where the FMUs can be simply connected together and the orchestrator can simply invoke, if it's an orchestrator for co-simulation, it can simply ask each FMU to do a step and exchange data. But in hybrid testing, the coupling algorithms are very important. And what these algorithms do is there are different possible scenarios where you might need a coupling algorithm, but we will focus on this one. And what the coupling algorithm does is collect for example, the velocity and displacement of each of the FMUs. Imagine this FMU may represent our metal bar, and this FMU may represent an arbitrary numerical structure. Now, if the metal bar is moving up at a particular speed, then it is expected, and this numerical substructure is also moving up. It is expected that the two movements are happening at the same time. They match exactly. But because these two are solved independently for some time, this is not always the case. So the coupling algorithm comes here as a way to find forces. So taking the output displacement and acceleration of each FMU, this coupling algorithm is responsible for finding forces that will compensate for these discrepancies, and therefore will ensure that after the data is exchanged and on the next step of the co-simulation, that these kinematic constraints will be satisfied. So we will describe next what the coupling algorithm does. But here, for example, for this scenario, the orchestration algorithm is fairly simple. It consists of simply stepping the two FMUs, exchanging the data between the FMUs and the coupling, then asking the coupling to do its thing to calculate its forces, and then exchanging the data from the coupling to the FMUs. So our coupling algorithm, the main goal is to ensure stability, and it does so in three main steps. First, it solves each system. It asks each system to evolve in simulated time independently. Of course, we have a physical subsystem, so this would actually run in real time. And after a step is made, then it calculates the coupling forces that enforce these kinematic constraints, and after it compensates, after finding the forces that compensate for this lack of communication in the first step, the FMUs receive these forces, and the FMUs themselves compute a corrected state for the next step. In the case of in our study, we have applied this. We have implemented this coupling algorithm in 3 different ways. We used 2 variants for FMI co-simulation interface, and we implemented it once for the model exchange interface. For the FMI co-simulation interface, we are able to the coupling algorithm was implemented as an FMU, and then we had to, of course, connect these force inputs into each numerical and physical subsystems. Now, the downsides is the FMUs. First, the coupling algorithm needs to be aware of the numerical algorithm being used inside the FMUs. It has to be numeric algorithm, and the coupling needs to know what alpha and beta constants of the numeric algorithm are. The FMUs themselves are also tied up to the coupling algorithm because they expect to receive this force, which is then internally going to be used to correct the internal state, except for the physical subsystem where slightly different algorithm is used. Then FMU step ordering is crucial, so the orchestration algorithm needs to be customizable. For the second variant, the only difference with respect to the first variant is that when exchanging data from the coupling to the numerical and physical subsystems, less data is passed on. So this is not so. This is more of a big deal for large-scale hybrid testing setups. With the model exchange scenario, the coupling FMU the coupling was implemented directly as part of the orchestration algorithm, and it results in more modular code because the FMUs do not need to know about the coupling. It's a lot easier because the corrections on the state can be done directly by the coupling. To conclude, we show that FMI interface version 2.0 is well suited for hybrid testing experiments, for standardizing hybrid testing experiments. Unfortunately, it is important that the importers are able to be customized in order to ensure that the stability is guaranteed by the algorithms. It's also important that there is some documentation on the FMUs that explain what the parameters are that are being used internally so that the coupling algorithm can be adjusted accordingly. Thank you.